Hello, my name is John Pither and I'm the CEO of Juxt. In this talk, we're going to be looking at Crux, the past, the present and the future. We're going to look at the past. How did Crux come to be? What's the origin of Crux? Why Crux? We'll also look at the present. What challenges are we facing right now? What features are we working on right now? And what does some of the code look like right now? The code that makes Crux tick, including some of the more hairy areas. We'll also look at the future of Crux. Where is Crux going? What does the roadmap look like? What challenges are we facing? And what decisions do we have to make? Crux is still an evolving product. So thank you very much. This is the first talk of Clojure. We're hugely excited to be here. It's going to be a fantastic conference. So let's get started. So what I want to show is the origins of Crux. Where did Crux come from? We talked about Crux being this unbundled database. So let's dive into the REPL, and I want to start showing you a few things, some of the core concepts. So this namespace here, I have a couple of protocols defined. The event log is like the first thing we want to unbundle. This is a sequenced store of events. It's as we learn facts about our business, as we come across these facts, we ingest them, and then we have them there forevermore in an event log. And we can store our messages, but we can also fetch our messages from a particular offset. This is kind of the way that something like Kafka works. We store our events onto an event log, and then we can say, from this offset, I just want to read all the events in sequence from that point. Then I've also got a KV store. And this is simply a place for me to store my events as I read them off from Kafka. And I want to show how with these two basic parts, we can start to get a semblance of a real working mini kind of database system that can suit some client requirements. This is where Crux came from. But I just want to show you for the purposes of demonstration. I've created a atom-backed event log. So this is like a fake Kafka. And all this really does is, instead of actually using Kafka for the event log, I'm just using an atom, which is essentially a vector. And I'm just storing my messages into this vector whenever you call store message. And then I've got a function here to say fetch messages with this offset. And as you can see, I've just got a rather cheeky drop while in there. So it derefs this atom, which gives you back a vector of messages. And then it just drops the first ones that are before this offset and then gives you the ones after that offset. So a cheeky little bit of Clojure here. And this, in 5 or 6 lines, is our pretend Kafka. So this is my atom-backed event log. And as you can see, if I go to my main namespace here, I'm creating one of those. And then I'm just storing some messages into it. And what I'm trying to demonstrate here is a sort of timeline of events. We released Crux 2019, so we spent a year, more or less, building it before we released it, about 2,500 commits. We released it at Clojure North, made it go live on GitHub, which was a good moment. James Henderson came in as our tech lead, and this is where we're at, Clojure 2020. So you can see I have a timeline, and I'm storing each one of these messages into my pretend Kafka. Right, so the offset is the date. And you could think about this as transaction time. And now if I wanted to, I could just say, look, we've got our pretend Kafka here. Fetch me all of the messages from a particular point in time. So let's just say 2019. I'm not interested in the 2018 stuff. I want all the events from 2019 onwards. And with any luck, this should give me those. And as you can see, we've got events from 2019. So Crux being released, James Henderson joining, and Clojure. So RocksDB is written by Facebook. It's tremendously scalable, and it's what we use in Crux in the unbundled sense to house our indexes. So we've got Kafka as the event log. When you write a document into Crux, it goes onto Kafka. It's persisted. That's the golden store, this event log. But then we use RocksDB to build up some clever bitemporal and content indexes that really enable you to do this general cross-purpose queries against. So I have my Rocks KV store here, which if I go to the namespace here, This is basically implementing that KV store protocol. I've got seek and I've got store. I've got seek and iterate, which I'll come on to. But just think about seek and store as the main two. So first of all, I'm going to fetch all of the messages from our pretend Kafka from a certain date. Here I'm saying 1500. And then I'm going to write them into our KV store. And that's what I'm doing in these 2 lines here. So now, after these 2 lines have been executed, our ROX KV store has all of the events inside of our pretend Kafka event log. So now I should be able to seek from at a point in time. And note that here, what I'm doing is I'm storing my keys as longs. So I have a function here to convert a Java instant into a long. And all this really does is that it just calls get time on it. So pretty simple for now. Get time gives you a long. I'm storing longs. Happy days. Now, inside of our KV store, these longs are actually indexed in order. So if I have some keys in here, so imagine we've got a key which is the long equivalent of 2010, and then the long equivalent of 2011, and the long equivalent of 2012. Because they're stored in order in ROX, and ROX is a KV store, I can say, well, I want to seek at a point in time. So if I seek about sort of 2011, and let's say it was a date in there, it's going to seek in between these keys. And in this actual case, I would get 2012 back. And that's kind of what's happening here. So if I do my seek on 2000, then the first event I get back for that is the pre-Crux prototypes, right? Because that's like the next thing on. So I'm seeking, I'm not hitting anything for that precise value, but then in a lexicographic way, it then gives me the next value on from that. And now if I wanted to say, well, I want to seek halfway through these dates, and we can see I've got these dates here. If I want to say, well, give me something around the actual Crux project time, so let's do 2009, let's do 2019, let's do June, then the next event on from that is James starting. James actually joined in September, but that lexicographic range query, that seek operation, is going to give me the next thing on from the date that I asked for, which is when James joined in September. So makes sense so far? So if you think about it, we're building up like a temporal index here. We've got the ability to seek at any point in time, and then it gives us the match closest to the point that we asked for. So we've kind of got a timeline in our KV store here, and we're seeking at points in that timeline. Well, I want to pose a question here, right, which is, but let's imagine that we were searching in a couple of days' time. So let's add in a string. Let's do an instant for 2020, and let's say we're sometime in December, and it's 06. We don't get anything back, right? So this is a kind of problem. Imagine you've got like a store of events, or imagine you've got a store of documents like trades or something, and you index them in a time-like way using this. You kind of want the ability to say, find me the latest thing as of now. And this doesn't do that for you. This will try and find the thing after now, the thing in the future which hasn't happened yet, which we've got no data for. So this index is kind of flawed in a way. We need to do something. One trick that we learned is to reverse the timeline. And we learned this earlier on, and it kind of helps you with this specific use case. So if I now do a bit not, then now, if I search for a date in the future, before we didn't get anything. But now, because we've reversed the whole timeline index, we're actually going to get the next thing, but in the past. So the index actually starts from the most nascent, the most recent bits of data in the timeline index, and then it descends through it as you go through the index in order as it's stored in ROX. So now we're saying, I want to seek at a point in the future, but then the next thing on from that is going to be the next thing in the past, which is this Clojure 2020 event. So now I can seek and iterate, just whack this in. So I'm seeking and iterating from this point in time, 2019, and then I'm going back through all of the events in the past. So here you can see we've got James, then we're going back into the past more, which is Crux release, then we're going back into the past more, which is Crux development starts, and then we're going back into the past, which is the pre-Crux prototypes. And this is kind of the way Crux still works to this day. We still have an index where we have instance in there serialized as longs, but then they are reversed. So the order is like a reverse order. Crux still works like this today, indexing timestamps as reverse longs that allows us to seek, to scan, and to iterate across the history of our database. Crux very much grew up from these primordial parts of an event log and a KV store, and then building up these timeline indexes. I hope you enjoyed this origin story. Let's move forward with the rest of the talk.
Hi there, I'm James Henderson. I'm the technical lead on Crux. I'm responsible for its day-to-day development and releases. I'm going to talk a little on the indices we keep in the query index store, how we use them in queries, and how they can be adapted for use in speculative transactions. In Crux, we make a distinction between content and bitemporal indices. The content indices keep a track of all the values an entity has ever taken. So if I lived in Scotland but then moved to England, these indices would contain both facts. They don't know anything about what entities had what values and when. The bitemporal indices store what version each entity has at any point in bitemporal time. And so given that Crux is a document database, we do this temporal resolution at the document level, rather than at the level of individual facts. And this version is in fact a content hash of the document's content. In practice, on the assumption that you often query more than one attribute from a document at any one time, this means we only need to do the bitemporal dance once. So, let's say we have a query where we're looking for all of the users living in England. We first go to the content indices. We have an index that will efficiently tell us all of the entities that have ever lived in England and their content hashes. And then we check the bitemporal indices. So did that entity have that content hash at the time we're querying for? If so, great, we have a match. And the case where we don't have a value in hand is similar. We have another content index that will efficiently tell us all of the entities that have ever had any value for the attribute lives in. As for how we store these indices as sorted prefix trees. So for the value in hand query, we have an index sorted first by attribute, then by value, and then by entity, an AVE index. In practice, we concatenate together the A, V, and E into one byte array. And when we then search for a value, we create a byte array containing A and V, and then use a byte array prefix seek to navigate through the tree to the first value after our search value. From this point, we can then scan through the tree, yielding different E's for our AV, until we hit a different prefix. So, John talked earlier about the unbundling of Crux. In this case, for the query indices, we're looking for an underlying storage provider that supports both fast seek to a key and then fast scan from that key. We also keep other content indices with various different variable orders to help out in the query engine. The bitemporal indices are ordered first by the entity ID and then by the bitemporal coordinates. The values in the KV for that contain the content hash of the entity at that time. Think about when we index a transaction. We have to update both the content indices and the bitemporal indices. We need to ensure that we update these indices atomically, although thankfully this is mostly handled by our underlying storage. We just need to make sure that we insert any changed keys in the same write batch. The indices themselves are purely additive. With the notable exception of eviction, we only ever insert keys. We don't ever update or delete. There are, however, a couple of cases that involve us needing to query the indices while the transaction is in progress. The bitemporal semantics require us to check the up-to-date history of an entity in order to update the bitemporal indices. Specifically, if a transaction contains multiple writes to the same entity at different points in the timeline. Similarly, during a transaction function authors can request a DB instance and make queries against it, and they expect to see the effect of the transaction so far. Thankfully though, because these indices are all sorted trees, they merge easily using a standard merge sort algorithm. Because we only use a few relatively low-level operations, seek, scan, and get value, it's relatively easier to abstract away the fact that we essentially have two underlying indices. Indeed, we have an implementation of a KV store, which combines a persistent on-disk index with a transient in-memory index. And the query engine doesn't know whether it's querying just the on-disk indices or with an in-memory index on top. This merging also means we can then make one large write to the persistent KV store at the end of the transaction, which turns out to be quite a performance boost over lots of smaller writes. Another fortunate consequence of being able to merge indices in this way is the ability to easily offer speculative transactions. Now, we introduced speculative transactions to Crux after a significant amount of user requests. It seems that to be the sort of feature that once you're aware of it and have used it a few times, you can't live without it. I say fortunate consequence because it turns out that once you have the ability to efficiently merge indices in this way, there's very little that actually needs to change internally to implement speculative transactions. A speculative transaction is simply an in-flight transaction that's never committed. If you're interested in finding out more about how Crux stores its data, you can have a look in the GitHub repo under the Crux core module, starting off with the Crux TX and Crux KV index store namespaces. Thanks.
Hello there, my name is Daniel Mason. I've worked at Juxt for just over a year and I work as an engineer on Crux. So today I'd like to talk about some recent changes that have been made to the HTTP server, and in particular the addition of JSON. So to give some background, the HTTP server was sat in an alpha state while the other modules had been moved into beta, and it was mostly because we wanted to make some improvements to commit to it as a stable API. To summarise, it was making endpoints more consistently named, handling parameters more consistently, doing errors in a standard way, and so on, and also ensuring that everything on the API was reflected within the HTTP server endpoints. And another element of this was content negotiation, which leads me on to JSON. So when standardizing the content negotiation, we decided to introduce both JSON and transit for input and output. And this was because beforehand, the only way to interact over the HTTP server was with Eden. Eden is and still continues to be very important throughout the rest of Crux, but we realized it's important to not be tied to a single format. And this seemed like a good first step towards JSON in the broader Crux ecosystem. The implementation itself was made much more possible by the addition of string IDs in documents. So now I'm going to give a quick demo using the Crux HTTP server and using JSON for input and output. I'm going to begin by taking a look at the node configuration we're going to use. As you can see, it currently only contains a Crux HTTP server on port 3000. And I start this node using the Clojure CLI tooling. Now that we have a node running, we can begin to send it requests. I'm going to send a request to the status endpoint asking for JSON back. And as you can see, we get a JSON document with some status information about the node. Now we can begin to start sending and requesting some data from the node. I'm going to send a set of documents. As you can see, they contain a first name, a last name, and an age. These documents are now sent successfully, and we get some transaction information back from Crux. Now we submit a query. As you may notice, the query is still in Eden, but we're asking for JSON back out. It's a simple query, and we're just looking for all of the documents whose age is above 40. And we get a set of documents back. Alongside the JSON changes, we added a few new functions to the HTTP server that were on the main API. This included some monitoring functions. So I'm going to have a look at the recent queries in JSON. And we can see some information about the last query that we just ran. Finally, we're going to get some information back about a particular entity. In this case, I'm going to have a look at Ivan and have a look at the history of Ivan. As you can see, only one thing is returned because there's only one piece of history for Ivan, but we get some information about that transaction alongside the document. So I hope that was useful. If you'd like to see more that you can do with the JSON API, please check out the docs and let us know if you have any questions. Thank you.
Hi, I'm Jeremy Taylor. I look after Crux from a product and community perspective, and I'd like to share a few stories from the community about molding and extending Crux to suit different environments. First up is this very unexpected yet very welcome Rust client for our HTTP endpoints by Julia and Ottavio. Of course, getting this to work first required them to get Eden RS off the ground. Impressive stuff. And if that wasn't enough, Julia also wrote up a similar client and Eden library for Elixir. Meanwhile, Severe Overflow has been busy concocting a Redis-backed transaction log and document store for when low latency is critical and RAM is lying spare. But perhaps most interesting is my conversation with Mitchell Kuipers a few days ago. He works for Avisi, a large development organization based in the Netherlands, where he heads up a product engineering team. They are one of our earliest and keenest users, owing to their love of using Datalog to accommodate their diverse schema.
So we are building Atlas CRM, and it's basically a CRM inside of Atlassian products. So we try to be the most integrated CRM inside of Jira, Confluence, etc. So you don't need another CRM system. With Crux, we have been running it for more than a year on server and data center. So that's the versions that customers host themselves. And we're currently in the process of moving to Crux on our cloud product. On the on-premise products of Atlassian, so for Jira and Confluence, if you host it yourself, you can install our plugin by installing a jar file, and that jar file gets deployed in an OCI container, and that has some really unique features. So it can do class loading at runtime and stuff like that, but it also has some issues. And one of the issues we ran into is that RocksDB or LMDB uses a C. It uses some native binaries. And if you reload our plugin, it will try to redeploy that native binary, and it just breaks down. It's just not workable on OCI, unfortunately. And we also ran into that to get to a database or somewhere where you can store a transaction log, we have to use a layer that Atlassian has created. So for the key value store, where you normally would use a RocksDB, we changed it to a full Java-based solution called Exodus from JetBrains. And for the transaction log, we created our own active objects implementation that's basically to conform to the abstraction layer that you get from Atlassian to integrate.
My name is Håkan Råberg, and I work with John on and off since 2005, and I also worked on Crux since the start. And during the early months of Crux, it was mainly written by myself and John. I was responsible for the initial architecture, which has now evolved into where Crux is today by James's team. These days, my role is to look at the future technical direction. So I spend most of my time reading papers, looking at various techniques that we can potentially use in Crux. These ideas are fed back into the team via discussions and occasional PRs. I also participate in the day-to-day architectural engineering discussions when needed, and I also code. Currently, I'm investigating 3 main areas for the future of Crux. The first idea is to move Crux towards an append-only column store architecture. This will make the raw data stored in Crux accessible in open format like Arrow. We also want to remove the assumptions about which index structures are needed up front. The idea is instead to rely on adaptive indexing tuned to different use cases at each node. The second idea is to separate storage from compute. By moving to these static columnar chunks, which we can store elsewhere, like in S3, we will avoid the need to keep all the data at each node all the time. This will make Crux much more elastic. It will also allow us to deal with data which cannot fit on a single node. Finally, there's of course temporality. Currently, Crux answers questions like, last year, what was my salary? Which usually referred to as a time slice or point in time query. But we want to unlock the full bitemporal power of data we store inside Crux and allow for temporal queries across ranges, joins, and intervals. This will allow for queries like, when was my salary at a certain level? Or what salary did I have in my previous role? This is related to the columnar and separating store from compute, as this will require new different ways of accessing the underlying data in efficient ways.
Hello. Types and schemas and tables and structures, these are the things that we build patterns on, patterns that we observe in the real world, patterns that we build our organizational knowledge upon. So if patterns encode organizational knowledge, why is Crux schemaless? Well, because the right schema for your application might not be the right schema for another application that's sharing the same data. Schemas are contextual. But still, in the future, we want to let you add schemas to Crux. So not just one schema, but potentially many. And not just one schema for all time, but the ability to evolve your schema as your understanding of your domain changes and as your requirements change. Not just one schema, but schemas evolving across the timeline. I really love this aspect of Crux. It's just like Clojure, that everything will be modeled as a succession of values across time. So we've been hard at work in our hammock and thinking about what it means to truly unbundle schema from the database. So with schema, we'll be able to add more ways of accessing data in Crux. We have SQL now, but soon we'll have GraphQL and OpenAPI in the future. So stay tuned, and we've got lots of announcements coming next year.
Thanks for watching this talk on Crux, the past, the present and the future from all of the Crux team at Juxt. We hope you enjoyed it. You can get more information on Crux at opencrux.com. We'll be around for some Q&A following on from this session at Clojure, and we hope you enjoy the rest of the conference.